All right, let's hit the other questions, starting on question number 3. All right, so here's question number 3. A sample of intestinal gas was collected and found to consist of 44% CO2, 38% H2, 17% nitrogen or N2, and 1% O2 by volume. What is the partial pressure of each gas if the total pressure inside the intestine was 818 torr? Well, this is Dalton's law again. Pressure total is going to equal the pressure of all these gas. And let's see, we got 1, 2, 3, 4. So pressure of the first gas plus the pressure of the second gas plus the pressure of the third plus the pressure of the fourth. So how are we going to do this? Well, if CO2 is 44%, what's 44% of 810? Well, to do that, we're going to take 810 and multiply by, we got to change the percent back to decimal. So multiply that by 0.44, moving the decimal place. And I get, this is 360. Again, this will be in torr, but it doesn't ask us to change anything, so that's totally fine. Now, we would do the same idea for all of them. And I'm just going to give you the numbers that I would get, so you can check those as you go. For hydrogen, I get 311. For nitrogen, I got 138. And then I get for oxygen, which is 1%, just about 8. Then if you wanted to double check, hopefully, if we had added all those up, that would equal 118. So that's the partial pressures of all of them. Not too bad. All right, let's look at number 4. Let's scroll this up just a little bit so it's a little bit easier to see. All right, so a metal canister contains a mixture of neon, argon, and radon. The neon exerts pressure of 0.24 atmospheres. Argon exerts 0.18 atmospheres. The total pressure of the container is 1.30. What is exerted by radon gas? Well, again, we're doing Dalton's law here. So pressure, the total, will equal the pressure of the 3 gases. This is pressure of neon, pressure of argon, and plus the pressure of radon. So here we know the total pressure, 0.10. It tells us the pressure of neon, 0.42. It also tells us argon, 0.18. So we just gotta do some math here to find that. So we can add those two up and minus it. And this one, we get a pressure for radon of 0.70. And it's atmosphere, so a good label would be ATM. All right. Pretty quick and painless, number 3 and 4. Let's move on to number 5. Okay, number 5. A 1-liter pressurized gas cylinder contains a mixture of oxygen and nitrogen. When the temperature is 25 degrees Celsius, the partial pressure of oxygen is 425 torr, and the partial pressure of nitrogen is 325 torr. What is the total pressure in the container at 150 degrees Celsius? Okay, now, a lot of stuff there. We got to ask ourselves, what are we using? What do we need to know? Well, it's asking for the total pressure. So we're talking about pressure. It gives us a volume of gas. That's great, but we really don't need anything to do with it. What is it asking? We're raising the temperature. So when we look through here, that volume's there, but it's not going to change. So volume will stay constant. We don't have to worry about volume. It gives us some partial pressures, and that's fine. We can add those together. So let's do that. 425 plus 325. That's our total, which 750, and that's torr. Keep our labels right. It wants the total pressure once it's raised. So this actually comes down to the pressure when we start over the temperature where we start will equal the pressure when we end divided by the temperature where we end. So there's a lot of stuff in there, but it actually just boils down to one of our first laws. So let's just put in the math here. 750 torr divided by our temperature. Now remember, we got to add 273 to this. So I'm going to do it here so you can see that I was going to add it. And then we want the total pressure, or P2, so we'll find that. And then we raised it, it says at 150, so 275 plus 150. And when I did my calculations, I get that new pressure. Now, even before, we should probably think about this. Temperature goes up. What's going to happen to pressure in this one? Yep, direct relationship. So it should go up. So it should go up. And I did get a number that goes much higher, 1,065. So there we go. There's question 5. All right, let's continue. And as always, I apologize for my writing. It's hard to write on here, but I think it's also the easiest way for you guys to be able to see me do these problems. Okay, question 6. What is the volume of a sample of nitrogen gas that has a mass of 43.5 and it is under a pressure of 785 torr at 23 degrees Celsius? Well, it gives us a lot. We want volume. We could, go back and think, hey, Boyle's law or something, but we have all sorts of stuff. So all else fails, we hit PV equals nRT. Now we're solving for volume. So I'm going to divide both sides by P. And when I do that, we get volume equals nRT over P. Now, again, I always got to remember or remind people that when we're using the ideal gas law, we have to make sure our units are correct. So when I start putting these things in, we got to change some stuff. So we're going to try to solve for V. And let's do the first one, N. We don't have the number of moles, we have the number of grams. So that's our first conversion, 43.5 grams. And it's N2. That will trick some people because when we do divide by our molar mass, we got to do 2 N's, and that would end up to being 28 grams to 1 mole. Mr. Foss's math, I get about 1.55. So I'm going to put that in there right now. We remember R is 0.0821. And then temperature here is 23 degrees, but we got to add 273 to that. So that gets us 293. Excuse me. 296. Come on, Mr. Foss. And that's all divided by the pressure. But pressure is in torr. So we're going to take that torr, and there's 760 torr to 1 ATM. And that gets us 1.03. So put that in the bottom. Once we do all our multiplying and dividing, we should get the volume of this gas to be 36.6. And again, our correct unit here would be liters of our N2 gas. All right. All right, let's continue. Let's finish these last two. Let's go. Let's go. I know you guys are excited. I'm excited. Clear. All right, anyways. Give us plenty of space. All right. How many liters of hydrogen, circle it because that's what we need, are collected by water displacement? It says water displacement. It is in bold. What does that mean? What do we have to use? Dalton's law. You got it. So we're going to use that. It gives us our temperature. It gives us our pressure. It gives us the number of grams of chromium. Be careful. Chromium is not the gas we're talking about. An excess sulfuric acid, great. Here we go. So our first thing, as you can see, is we got a balance. We're not going to waste a lot of time on that. That's 2, 3, 3, 1. So we want to find liters in here. Again, we're going to use PV equals nRT. Now, from the last one, we know what we need to do. We're going to have volume equals nRT over P. So now we got to find all this stuff. So we can do it any way we want. I kind of go in order, the N, R, T, and then P. So let's find N, the number of moles. Now, again, we're asking about hydrogen. This is a mistake people will make when they start, is they just try to find moles of chromium, but we don't want moles of chromium. We need moles of the hydrogen gas, hence the balanced chemical equation. I give us chromium up here. It is 52.0 grams to 1 mole. And there is 2 moles of chromium to 3 moles of hydrogen gas. And again, that comes from our balanced chemical equation. When I solve for this, I get the number of moles to be 0.0355. We know what R is. Temperature, let's just do this right up here. It says 25 degrees. So 273 plus 25 gives me 298. And so now we have pressure. This is our last one. And remember our key here, water displacement. So we got to use Dalton's law. It tells us our pressure here. And now this pressure is our total pressure. So right down here, we have 742. Actually, let's do it this way so we can visualize it a little bit better. We have our pressure total again is going to equal our 2 gases. Now it's over water, so we have to have water in there and the gas we're talking about, and this is hydrogen gas. So now let's put these in. 742 is our atmospheric pressure. What is our water pressure? Yeah, this is the one that we got to go back to our top of the paper and find that. Well, our temperature is 25. So if we look at 25, we're going to find that that is 23.8. I put that where hydrogen is. We should put that to where water is. 23.8. So to find the pressure of hydrogen gas, we're going to minus that. So I get a pressure of hydrogen gas to be 718.2. And again, we want to make sure of our units. This is millimeters of mercury. We don't want that, so let's change it right here to 760 millimeters of mercury equals 1 ATM. And when I do that, I get 0.945. So as you can see, in a lot of this is knowing what unit you're in and doing a lot of those conversions. All right, now I'm going to plug all my numbers in over here to the left. We know the number of moles, so let's do this. V will equal 0.0355 times R, 0.0821 times our temperature, 298, all divided by that pressure of the gas, that hydrogen gas, 0.945. When I finally finish my math, my number is 0.919 liters of hydrogen gas. Ooh, that's a good one too. I like that it uses all that stuff up. All right, let's keep going. Last question. All right, so last question. Calculate the molar mass of a liquid when vaporized at 98 degrees Celsius, 725 torr, and gave 125 milliliters of vapor with a mass of 0.625. Well, in this one, it says molar mass, so that's what we got to get. And our label for molar mass is grams divided by moles. So right there, we got half that problem. We got the number of grams, 0.625. We got to find the number of moles. Well, the only way to find moles is through PV equals nRT. Doing our algebra real quick, we're going to divide both sides by RT. And that will give us, or leave us, what our mole will be. All right, so let's see what we have. Our pressure, yep, we got to change it again. 756 torr. Divide that by 760. I'm going to go a little faster on this. And that gives me 0.995. Our volume of gas, we have to change that one, but that one's easy. We're going to move the spot 1, 2, 3. R is a constant, and then we have temperature. And again, a lot of these we're just getting used to doing just off the bat. That's 98, so I get this one to being 371. So let's plug all our numbers in. We got a pressure of 0.995, a volume of 0.125, divided by our constant, 0.0821, times our temperature, 371. When I'm all done with this, I get 0.00408. Now, a lot of times we get used to just doing these and then we'd stop right there. But we got to remember what the question asked for is molar mass. So we got to take that number and divide it. So when I do that, I get a molar mass of 153 grams per mole. All right. Again, I have to apologize the sloppiness of it. Just the easiest way to be able to kind of go through the problem and show it. Hopefully all my calculations are correct. Good luck, and we'll see you soon.